the insane engineering of SpaceX Raptor engines. But before we start, I would want you to hit that red subscribe button so that you never miss out on any of our videos. So guys, Raptor is a family of full-flow staged combustion cycle rocket engines developed and manufactured by SpaceX. For use on the in-development Starship fully reusable launch vehicle, the engine is powered by cryogenic liquid methane and liquid oxygen, rather than the RP-1 kerosene and LOX used in SpaceX's prior Merlin and Kestrel rocket engine. The Raptor engine has more than twice the thrust of SpaceX's Merlin engine that powers the current Falcon 9 and Falcon Heavy launch vehicles. Raptor is being used in both stages of the two-stage to orbit Super Heavy Lift Starship System launch vehicle, which will supersede Falcon 9 and Falcon Heavy. Starship will be used in various applications including Earth orbit satellite delivery, deployment of a large portion of SpaceX's own Starlink mega constellation, and the exploration and colonization of Mars. The Raptor engines first flew on the Starhopper test vehicle in July 2019 and began the first full-flow staged combustion rocket engine ever flown. As of August 2020, Raptor holds the record for the highest combustion chamber pressure ever reached by an operational rocket engine at 330 bars, surpassing the record held by the RD-701 rocket engine at 300 bar. Now, since the founding of SpaceX in 2002, the company has developed 4 families of rocket engines: Merlin, Kestrel, Draco, and Super Draco, and is currently developing another rocket engine, Raptor, and after 2020, a new line of Methox thrusters. In the first 10 years of SpaceX, the company developed a variety of liquid propellant rocket engines, with at least one more of that type under development. As of October 2012, each of the engines developed to date, Kestrel, Merlin 1, Draco, and Super Draco, had been developed for initial use in the SpaceX launch vehicles. Falcon 1, Falcon 9, and Falcon Heavy, or for the Dragon capsule, each main engine developed by 2012 has been kerosene-based, using RP-1 as the fuel with liquid oxygen as the oxidizer, while the RCX control thruster engines have used storable hypergolic propellant. In November 2012, at the meeting of the Royal Aeronautical Society in London, United Kingdom, SpaceX announced that they plan to develop methane-based engines for their future rocket. These engines would use staged cycle combustion for higher efficiency, similar to the system used on the former Soviet Union's NK-33 engine. By mid-2015, SpaceX had developed a total of 9 rocket engines architectures in the first 13 years of the company's existence. Now we're going to start with the super quick physics lessons, but bear with me, we'll dive in and get plenty of nitty-gritty details. We'll leave no stone unturned, and by the end of this video, hopefully, you'll have a strong grasp of how rocket engines work, the different versions of liquid-fueled rocket engines, why methane is a valid choice for fuel, and you'll know exactly how the Raptor engines stack up against some other popular rocket engine. So guys, rockets are basically just propellant with some skin around it to keep it in place, and they have a thing on the back that can throw said propellant really fast. And to way oversimplify it even more, the faster you can throw that propellant, the better. The easiest way to do this is by storing all the propellant in your tanks under really high pressure. Then put a valve on one end of the tank and propelling nozzle that accelerates the propellant into workable thrust. Done. No crazy plumps or complicated systems. Just open a valve and let it rip. This is called a pressure-fed rocket engine, and there's a few main types: cold gas, monoprop, and bipropellant pressure-fed engine. You'll often find these used by reaction control systems because they're simple, reliable, and quick. But pressure-fed engines have one big limiting factor. Pressure always flows from high to low, so the engine can never be higher pressure than the propellant tanks. In order to store propellant under high pressure, your tanks will need to be strong and therefore thicker and heavier. Look at composite overwrapped pressure vessels, or COPVs. They're capable of storing gases at up to almost 10,000 psi, or about 700 bar. Despite this, there's still a limited amount of propellant and pressure they can store. This does not scale up very well when you're trying to deliver a payload to orbit. So smart rocket scientists quickly realized in order to make the rocket as lightweight as possible, there's really only one thing they could do: increase the enthalpy. That would be a great 90s metal band name, Enthalpy is basically the relationship between volume, pressure, and temperature. A higher pressure and temperature inside the combustion chamber equals higher efficiency, and more mass shoved through the rocket engine equals more thrust. So in order to shove more propellant into the engine, you could either increase the pressure in the tanks or just shoot the propellant into the combustion chamber with a high-powered pump. The second option sounds like a good idea. But pumps moving hundreds of liters of fuel per second require a lot, and boy do I mean a lot of energy to power them. So, what if you took a tiny rocket engine and aimed it right at a turbine to spin it up really fast? You could exchange some of the rocket propellant's chemical energy for kinetic energy, which then could be used to spin these powerful pumps. Welcome to turbo pumps and the staged combustion cycle. But you still got some limiting factors, like how high pressure always wants to go to low pressure and how heat has the habit of melting things. So you've got to keep all these factors in check while trying to squeeze every bit of power out of your engine. Now, there's actually a lot of cycles here we could talk about, but I'm going to stick with the three most common, or at least the three that matter the most when putting the Raptor into context. We have the gas generator cycle, the partial flow stage combustion cycle, and lastly, we'll look at the full flow stage combustion cycle. And perhaps in a future article, I'll try and do a full rundown of all liquid-fueled rocket engines, including fun new alternatives like the electric pump-fed engines seen on Rocket Lab's Electron rocket. So let's start with the gas generator cycle, otherwise known as the open cycle. This is probably one of the most common types of liquid-fueled rocket engines used on orbital rockets. It's definitely more complicated than a pressure-fed system, but it's fairly simple. Well, at least compared to their closed-cycle counterparts. Now I'm going to way oversimplify this so it's as easy to grasp as possible. In real life, there's literally dozens of valves, a hive of wires and extra small pipes, helium to back pressure the tanks, fuel flowing through the nozzle and the combustion chamber to cool it, and an ignition source for the pre-burner and the combustion chamber. But again, for the purposes of making this simple and as digestible as possible, just know there's a lot of stuff missing, but we're focusing on the flow of these engines to get that concept down. Then, once you grasp these simple versions, it'll be much easier to look at one like this and not have your head explode. The gas generator cycles work by pumping the fuel and oxidizer into the combustion chamber using a turbo pump. The turbo pump has a few main parts: a mini rocket engine called the pre-burner, a turbine connected to a shaft, and then a pump or two that push propellant into the combustion chamber. You might hear the turbo pump assembly called the power back because it really is what powers the engine. In the open cycle system, the spent propellant from the pre-burner is simply dumped overboard and does not contribute any significant thrust. This makes it less efficient since the fuel and oxidizer used to spin the pumps is basically wasted. Guys, now the funny thing about the turbo pump is that it kind of has a chicken and egg syndrome situation that makes it pretty difficult to start up, since the pre-burner that powers the turbo pump needs high pressure fuel and oxidizer to operate. So the pre-burner requires the turbo pump to spin before it can get up to full operational pressure itself, but the turbo pump needs the pre-burner to fire in order to spin the turbo pump, but the pre-burner needs the turbo pump, etc. etc. This makes starting a gas generator tricky. There's a few ways to do this, but we don't need to get into all of that in this article. That sounds like a fun topic for a future article though, so back to the turbo pumps. Remember, pressure always flows from high to low, so the turbo pumps need to be a higher pressure than the chamber pressure. This means the inlets leading into the pre-burner is actually the highest pressure point in the entire rocket engine. Everything downstream is lower pressure. Guys, if you will look at SpaceX's Merlin engine, which runs on RP-1 or rocket propellant 1 and liquid oxygen, you will notice how black the smoke is coming out of the pre-burner exhaust. Why would it be so sooty compared to the main combustion chamber, which leaves almost no visible exhaust? Well, that's because rocket propellant can get super hot, like thousands and thousands of degrees Celsius. So to make sure the temperature isn't so hot it melts the turbine and the entire turbo pump assembly, they need to make sure it's cool enough to continually operate. Running at the perfect fuel and oxygen ratio is the most efficient and releases the most energy, but it also produces a crazy amount of heat. In order to keep the temperatures low, you can run the pre-burner at a less than optimal ratio. So either too much fuel is known as fuel-rich or too much oxidizer or oxygen-rich. Running as RP1 engine fuel-rich means you'll see some unburnt fuel appearing as dark clouds of soot. The highly pressurized unburnt carbon molecules bond and form polymers, which is a process known as coking. This soot starts to stick to everything it touches and can block injectors or even do damage to the turbine itself. So yes, that's all for today. I hope you liked the video. If you did, make sure to hit that like button and subscribe to the channel so that you never miss any amazing video from us.